Welcome to Chapter 8 on earthquakes. In Part 1, we'll look at faults and earthquake waves and the mechanics behind earthquakes. And in Part 2, we'll look at earthquake hazards. Now, I typically show this image at the beginning of the lecture on earthquakes. And here we have a double-decker freeway that has collapsed. You can see there's actually the bottom deck there. And then here we have the top deck that has collapsed down onto it as a result of the earthquake. Now, I often ask students after I show them this image to guess where this photo was taken. And invariably, there'll be lots of students that'll guess somewhere in Japan or maybe in China, elsewhere in Asia. But actually, this photo is taken in California. So this is the result of the 1989 earthquake in the San Francisco area. And this is the part of the Nimitz Freeway that collapsed in Oakland. And so in this part of Oakland, again, to conserve space, to not need to take up as much land in a urban area, they selected to build a double-decker structure. But then this double-decker structure collapsed during the earthquake. And there's some specific reasons why this section collapsed that we'll look at as we go further into earthquake hazards. Now, looking at some other earthquakes, this is one in China back 12 years ago now, so back in 2008. This is a very large quake, so this is a 7.9 in magnitude. And altogether, this killed around 60 or 70,000 people. Now, the reason why so many people died in this earthquake, again, the size does matter, but what matters more is the type of construction in the area. So you can see there's lots of building collapses, as we can see in each of these images. But I want to call your attention to the image on the right, where you see a portion of the structure that just a little corner of the building that did not collapse, the rest of it did. And you can see that this was a multi-story building that collapsed. So we see that there's 4 floors there that did not collapse. There's definitely some more below. So this was at least a 5 or 6 story building that collapsed. And when you get large structures like that failing during an earthquake, that is what kills people. There's an old saying that earthquakes do not kill people, buildings do. And this is a great example of that. Now that Chengdu earthquake, again, Chengdu is here on this little inset map. The epicenter is actually right there, and you can see this actually right along the edge of the Tibetan Plateau. And so this is related to the continuing impact of India into mainland Asia. And again, it's all part of that plate tectonic setting. Now, to contrast this with another earthquake, this is one that happened in Mexico back in 2003, so near Colima. And this was also a large earthquake, so about a 7.8 magnitude, so almost as big, practically the same size as what happened in China. But in this case, only 29 people were killed. Not 29,000, 29. And so there's something that accounts for the drastic difference in the death toll and the overall damage in Colima, Mexico versus Chengdu, China, even though these earthquakes are practically the same size. And so here we see some of the damage in Colima. And yes, you can see there's some buildings that collapsed. This structure, looks like we got some collapse onto that car there. You can see several other structures that either collapsed or were extensively damaged. But this shows the drastic difference. So here, most of these were single-story structures. So single-story homes and other buildings, maybe a few 2 or 3-story structures, but not very many, as opposed to a more densely packed area that had 5, 6-story buildings or 10-story buildings falling. The difference between these two was the population density. So even though we did have some very severe damage and lots of building collapses, they were smaller buildings with a lot fewer people in them. And that's what accounts for the far lower death toll. Now, probably the best example of how the quality of construction can influence the death toll is what happened in Haiti back in 2010. And so this was a 7.0 earthquake. Again, it's a strong earthquake, but only about, well, a little more than a tenth of the size of what happened in China with the Chengdu earthquake. But here the estimated death toll has ranged as high as 230,000. Now, again, we should emphasize that this is the estimate. One of the big problems is that after the earthquake happened, nobody's really sure how many people actually died. And some people say, hey, well, it should be easy, just count the bodies. Unfortunately, when you're dealing with a death toll this high, it's not the easiest thing to count the bodies in a timely manner because you need to bury them very quickly before things get rather unpleasant. And again, it's just the harsh reality of a disaster on this scale. That once you're dealing with death tolls in the thousands or even hundreds of thousands, potentially in this case, you don't have time for individual funerals in a lot of cases. You often have to resort to mass burials. And in some cases where there's not even enough time for that, if there's not enough manpower or heavy machinery to dig mass graves, in some cases they've had to resort to mass cremations. Because when you're dealing with an extraordinarily high death toll, you have to deal with the dead in a very timely manner before things get really unsanitary and unpleasant, to put it mildly. Now, revisiting the quality of construction issue. If we look at this wreckage here, we can see that this is actually a 2-story building because, well, at least a 2-story building. More than that probably, because we can see remnants of some stairs up there that are going up to another level. So first off, if we imagine that this is the ground level, this would be the 2nd story. There's at least a 3rd story going up further than that, but again, it's all crumbled and it's just gone. Now, this can be very deadly to anybody inside a building like this that is collapsing. The other thing I want to show you to emphasize in this image is look at what they are using as reinforcement in this masonry construction. Now, these are not the thick rebar that would have been used here in the US or much of the rest of the developed world. You can see that in comparison, these are relatively thin wires in comparison. This is not standard rebar, and it was just not strong enough to reinforce the structure. And when it shook, this building just collapsed. Now, there's a couple of reasons why these buildings in Haiti were built the way they were. First off, we need to understand that Haiti is the poorest country in the Western Hemisphere. And so in a lot of cases, the people just couldn't afford better construction materials. Secondly, the government of Haiti over the last, well, 100 or more years has been notoriously less than stable. And so if you imagine that, first off, if you have the barely functional government, are you going to have proper building codes to prevent buildings like this from collapsing? Second, even if you do have good building codes, if the government itself is barely functional, how well they're going to be enforced? And so because of factors like that, combined with the poverty of much of the people in the Port-au-Prince area of Haiti, these buildings were just not strong enough to withstand an earthquake. And so remember the old adage, earthquakes do not kill people, buildings do. Now, this is not, or this was not limited to, say, the slums of Port-au-Prince, but this was the presidential palace. So you can see it there again a few years before the earthquake, and then, of course, on the bottom after the earthquake. So you can see that these domes, the domes themselves are fairly strong structures. But you can see that most of this floor, again, the second floor of the building just collapsed. And in this case, the entryway, this former grand entryway, the column supporting the dome just buckled. The dome itself stayed intact, but the supports underneath it were not strong enough to hold it up once the earth started shaking. Now, to put a few recent earthquakes in context, so this is stuff from the last mostly 20 or 30 years or so. The Northridge earthquake of 1994 in Southern California, that was about a 6.7 and killed 60 people. The San Francisco earthquake of 89, again, that was the freeway collapse that we looked at the beginning of the lecture. The death toll there was 63. About 2/3 of them, though, were on that collapsed freeway. 7.3 in Landers, California, killed 2 people. Now, yes, this was a little stronger earthquake, but it was out in the desert, very sparsely populated area, and so there's just fewer people to kill, and so that is the main reason why the death toll was so low. And then we look at 7.6 in Taiwan back in 1999. That killed about 2,400 people, so a bit higher death toll. Again, largely because of the denser population in that area. And then the Haiti earthquake, again, this is an estimate, I should say, not the estimate. Estimates for the death toll have ranged anywhere from about 80,000, 70 or 80,000 up to over 230,000. Again, when you're dealing with the death toll that high, sometimes it's hard to get an accurate count because you just have to bury the bodies fairly quickly before things get really unpleasant. To compound that problem, remember that Haiti had at times, barely functioning government, and so public records were not necessarily very complete. And so in some neighborhoods, there wasn't even an accurate tally of how many people even lived there before the earthquake. And so, yes, you could say, well, just count the survivors and see who's missing, but they didn't always know how many people were missing, or if some of the people among the missing were using it to get away from a less than desirable situation or whatever else. Again, lots of problems can happen as a result of these earthquakes. But to contrast Haiti with another earthquake of the same size, again, both 7.0 in the same year. Haiti, death toll anywhere from 70 to 230,000. And in New Zealand, death toll was 1. And that person wasn't even crushed in a collapsing building, even though there was some significant damage in some areas. But they died of a heart attack. And so it's kind of an indirect death, if you will. But A year later, there was an aftershock. Now, the aftershock was smaller than the main event because, again, it's an aftershock, not a new earthquake. But because there are many buildings that were already severely damaged, they're not yet accurately, not yet fully repaired. And this aftershock was actually closer to the city of Christchurch. The death toll here was over 180, even though the main event, which was actually a little further away from the city, did damage a lot of buildings but didn't collapse as many as the aftershock did. It only killed one. So you still have to worry about aftershocks, again, mainly because of buildings that are already damaged but are barely standing and just need a little extra nudge to get them to topple. Now, looking at another earthquake during that same year as Haiti and Christchurch, New Zealand, there was a big, massive earthquake along the coast of Chile. That was an 8.8 in magnitude. Now, at the time that this happened, it was the 5th largest earthquake ever recorded. It's now the 6th because, again, just a year later, there was a bigger one in Japan. But this did cause a bit of a tsunami. There were several hundred, at least, that were killed. There were some accusations that the Chilean government was releasing inaccurate death numbers in order to make it look like it wasn't as bad, so that it would propaganda, if you will, to make it look like they were in better control of the situation, even though, again, lots of people died. And then Japan. So in 2011, there was a huge earthquake in Japan, 9.0 in magnitude. And the most notable thing about this is that it caused a tsunami. Now, the tsunami damaged several nuclear reactors, and the death toll from this event was somewhere in the neighborhood of 15 to 20,000. So now that a lot of the missing people are accounted for and still alive, the most put it around 16,000. But most of the damage is done by the tsunami, and we'll take a little further look at that as we look at some of the seismic hazards. Now here we're looking at a few of the earthquakes that have happened in just the last few hours. So this is as of Thursday morning, May 28th, and so you can see the universal time there. Yes, we see lots of small earthquakes. These are all the quakes around the world above a 2.5 in magnitude. And so you can see that in the last few days, yes, we have had quite a bit of activity in Nevada, so near Tonopah. There's another one from Nevada, another one from Nevada. And so, yes, they've had a bit of activity in Nevada, a string of small quakes, and lots of other activity as well. Now, again, this is all of the earthquakes in the last few hours around the world above a 2.5 in magnitude. And we can see that, well, within the last few hours, it looks like the biggest quake, let's see, it looks like there's a 5 there near the South Sandwich Islands. So that is very southern Atlantic, if I remember correctly. And another 5 near Papua New Guinea. And so, yes, if we look back on some other days, we should see some larger stuff. But again, this is just the largest stuff in the last few hours. Now here we see a full week of earthquake activity across the lower 48 states and much of North America. But what you should realize is that, yes, there's lots of activity along the San Andreas Fault in California, so lots of earthquakes there. And that even though we haven't had very big earthquakes, again, we have had some stuff in the last year or so here in Utah, we do tend to get a fair amount of small earthquakes fairly regularly. And then every few decades to few hundred years, we may get some larger ones. But you can clearly see again where the plate boundaries are, but also where some of the other major fault systems are, primarily in the western US, and then some other interesting spots in the interior of the plate. So this animation shows some of the larger earthquakes that have happened last few hundred years. And let's see, there we go. And you can see there's a few there. Again, this is going by chronology, but you'll pause on stuff that's happened for pretty much from 1990 up until 2011. Originally, this was a longer list, but the computers we had on campus at the time would crash if I had a longer list than what we have here. But you can see a few interesting ones. Again, over in Iran in 1990, 7.7 in magnitude, killed around 40,000. And so a high death toll from that. 400,000 left homeless from that. If we look at some stuff in the US, so in 1994 in California, magnitude 6.6, so strong earthquake, only about a tenth of the size of what happened in Iran, but this one killed about 61. And just a year later, on the same date, we had one that happened in Japan, just barely slightly bigger in size, but not dramatically, but it killed over 5,000 people. But looking at some of the really big ones, and so back in 2004, Sumatra, this was, depending on the margin of error, either the second or the third largest earthquake ever recorded. So this is a massive quake, caused a tsunami that spread across the Indian Ocean that struck many thousands of people unawares. And altogether, the death toll was well over 200,000 people. Now, if we contrast that to what happened in Haiti, again, Haiti was a 7.0, and depending on whose numbers you use, could have had a similar death toll. And again, that shows the difference in the importance of having strict building codes and, well, adhering to them. But it's the buildings in Haiti that caused such a dramatically high death toll, even though the earthquake was only about 1% the size of what happened in Indonesia. Now, so that's something that we really need to watch out for when we look at earthquake hazards. Okay, so now looking at the causes and some of the mechanics behind earthquakes. Now these two maps show all of the earthquakes over about a 6 or 7 year period back in the 60s. And of course, we had lots of renewed interest in studying earthquakes around that time because just previous to that was the introduction of the theory of seafloor spreading and plate tectonics. And also in 1960, we had the largest earthquake ever recorded that was along the coast of Peru, of Chile. And so lots of interest in studying seismology at the time. So we had some really good data that continues to this day. But if we look around, again, you can clearly see something going on around the Pacific Ocean. So you can clearly see the ring of fire. Now, again, the top map is showing all of the earthquakes between 1961 and 1967, while the bottom map is showing the earthquakes that are deeper than 100 kilometers. And so if we compare the maps, we can see some things that show up on some, but not the other. And so on the map for all the earthquakes, you can see the position of the mid-ocean ridges, and they were just showing the mid-Atlantic ridge. And those have relatively shallow earthquakes, but those do not show up on the map for the deep earthquakes. What does show up on the map for the deep earthquakes are the subduction zones. So we have the subduction zones there, and up in Alaska through Japan, Indonesia, down to New Zealand, another subduction zone there, and then some of the other convergent plate boundaries. And again, we do have a little gap here. Again, we'll talk about that with the Cascadia subduction zone and so forth. But right now we have highlighted the major convergent plate boundaries around the world. And you can see that most of those are around the Pacific Ocean. And so again, most of the earthquakes where they're dealing with these subduction zones and the other convergent plate boundaries, or whether we're dealing with the mid-ocean ridges and or the transform plate boundaries and so forth, the vast majority of the earthquakes happen along plate boundaries. But yes, there are some others that come in here and there that we'll also talk about. Okay, now this table shows the 16 largest earthquakes ever recorded. So pretty much, since the turn of the 20th century up until the present day. And you can see up top, again, we have the largest one in Chile, 9.5 in magnitude. So this is a huge, massive earthquake. Now, one thing that we need to note is that the magnitude, whether we're looking at the moment magnitude scale or the Richter scale, this is a logarithmic scale, so every whole number represents a tenfold increase. So that 9.5 is 10 times as big as an 8.5. So again, remember it's logarithmic. Now, if we look at the location for where all of these are, again, Chile in 1960, that 9.5 earthquake, that one is along a subduction zone. Prince William Sound back in 1964, also a subduction zone. Sumatra, again, here they have it ranked as number 3, but subduction zone. And then let's look at the trend here. Subduction zone, subduction zone, subduction zone, subduction zone, subduction zone, subduction zone. Do you see a trend yet? Now, then at number 10, not a subduction zone, but still a convergent plate boundary. And then we have subduction zone, subduction zone, subduction zone, subduction zone, related to a subduction zone, and then subduction zone. So of the 16 largest earthquakes ever recorded, all but one of them are on a subduction zone. The one that is not is on another collisional convergent plate boundary. And so if we want to know where the biggest, most powerful earthquakes are going to occur, just look at the convergent plate boundaries. And again, most of these are around the Pacific Ocean. So here we have a map showing where those 16 earthquakes are. And you can see that, yes, most of them are around the Pacific Ocean or close to that. And then we have that one in Tibet, and yes, a couple over here in Indonesia. But Indonesia we can throw in with the Ring of Fire because it's close to the Pacific, and it's just kind of a little side extension of that. We'll treat it like that. But again, if we want to know where the biggest earthquakes are most likely to occur, just look at the Pacific Rim, look at the Ring of Fire. Now, part of the mechanics that we have with the earthquakes is what's called the elastic rebound theory. And so this is how we can explain some of the deformation that we see with earthquakes. Now, the earthquake itself is dealing with brittle deformation along a fault. And so right along the fault, things are cracking, failing brittly, and you get motion on one side in relation to the other. However, before it fails brittly, it can be deforming ductily. And this is a very important thing to understand, is that as the stress builds up, you can get ductile deformation that then will eventually fail brittly. Now, as a little demonstration of how that happens, we often use something like a yardstick or other stick to show how, again, as the stress is building up, you will get Ductile deformation will start to bend. But as it finally bends too far, either, again, the stick will crack or it'll slip loose, and in the process it will straighten out, and most of that built up strain will be released as things straighten out, and that's what we call the elastic rebound theory. Now, the elastic rebound theory is important in understanding some of the deformation that we often see in coastal areas after an earthquake. And so if you imagine that this overriding plate is starting to bend and flex as a result of that strain building up, as that strain is released, areas that have bent a little more, they'll straighten out, and so you may have some areas that straighten out downward, and so that flexure will cause subsidence of portions of the coastline, while areas along the sea floor that straighten out, they may be uplifted along the sea floor. Now, the real problem is, again, this uplift along the sea floor, this can displace huge volumes of water that has to go somewhere, and this is what generates the tsunamis. Okay, so reviewing a few basic earthquake terms. An earthquake, again, is just the shaking that happens as there's movement along the fault, as all that strain is being released. Now, the place where the earthquake is actually originating, this is referred to as the focus. It's also called the hypocenter. And so this is where the earthquake is started along the fault, again, somewhere deep below the surface. Now, the point directly above that, that is referred to as the epicenter. And so that's what you're actually more likely to hear about on the news, because, again, while we can get to the epicenter, while the hypocenter might be miles below the surface. And then another concept that we need to understand is what's called a seismic slip. And so some faults may move very slowly and gradually without lots of major earthquakes, even though they may be moving as much as some other segments of the same fault that, well, lock up for longer periods of time and build up lots of strain. Now, there's actually a segment of the San Andreas Fault that is moving aseismically, and recently was discovered that the rocks along that particular segment of the fault are extraordinarily weak, and so they just can't build up lots of strain, and so that's why they fail more slowly and gradually without building up strain and without producing big earthquakes. Okay, so here we see a little diagram showing, again, the fault plane there. There we have the focus. Again, that is where the earthquake is started. So again, the focus or the hypocenter. And then on the surface directly above that, that is the epicenter. Now, if the fault plane is inclined like we see here, the epicenter will not be where the fault breaches the surface. And so it can be sometimes a bit displaced from the actual fault trace. Okay, a few other terms and then types of faults. Again, a fault is any planar break in the rock where there's movement. That's where the earthquakes happen. Fault scarps are anytime you have vertical displacement. And so you may have one side being pushed up in relation to the other. Now, if you have an inclined fault plane, the side that is on the bottom is called the footwall, and then the side that is on the top is called the hanging wall. So if you imagine that the fault plane is inclined like that, this would be the footwall. Again, pardon my lack of penmanship with the mouse there. And then this side would be the hanging wall. So if you imagine that there's a tunnel right along the fault plane, and there's a hook on the ceiling, you could hang your jacket on the hanging wall, but your feet are on the footwall side. Okay, so looking at fault types, we categorize these based on how the footwall and hanging wall are moving in relation to each other. Now these first two, normal fault and reverse fault, we categorize these based on, again, these are inclined fault planes, and so we're looking at how the hanging wall is moving. And so for the normal fault, that hanging wall is dropping down relative to the footwall. And so this is in relation to tensile stress. So the crust is being stretched out. For a reverse fault, the hanging wall is pushing up. It's being pushed up relative to the footwall, and this is being caused by compressive stress. Now with a strike-slip fault, you don't really have too much vertical movement here, but it's more shear stress. It's more side to side. Now the San Andreas fault is a great example of a strike-slip fault. Now the last one here on our list is a thrust fault, and this is usually defined as a very low angle reverse fault. Now here we have 15 degrees, but the number of degrees don't matter too much because I've checked multiple sources and found multiple answers, but what counts more is the amount of overlap you get with a thrust fault. And so you have lots of compressive stress with a thrust fault. Okay, so looking at some simple block diagrams. So here you can see the hanging wall being dropped down relative to the footwall. You can see how this darker layer has been offset there, has been dropped down. Whereas for the reverse fault, the hanging wall has been pushed up. And so you see now that there's an overlap there, while over here there's a gap in that black layer. And so a normal fault, you have extension of the crust, while reverse fault, you have compression of the crust. And then strike-slip fault, again, usually we think of these as being more or less vertical. They can be inclined, but that doesn't matter because most of the movement is lateral, and so we have more shear motion there. And then a thrust fault is just that really low angle reverse fault where you typically find lots of overlap. Now looking at some examples, some real world examples, here we have the fault scarp from the 1959 earthquake in Montana near Hebgen Lake, which is just outside of Yellowstone. And so you can see up over here, there's a person for scale. And you can see this tall fault scarp. And so we're looking at, depending on where you measure it from, this fault scarp ranges anywhere from 10 to 20 feet high. And so basically the hanging wall dropped down in some places as much as 20 feet. Now here we see the fault trace for the San Andreas fault from the 1906 San Francisco earthquake. And so fortuitously, somebody just happened to build a fence right across the San Andreas. And so you can clearly see the offset that happened as a result of the earthquake. And so of course this side moved that way, while that side moved that way relative to the other. Now this is not the area that had the largest offset from this earthquake. There was a place further north of San Francisco that had an offset as much as 20 feet or more, a vertical offset that ranged over several miles, moved that much. Okay, so looking at seismic waves. Okay, there are multiple types of seismic waves. Now the first two we're looking at here, what are called body waves, because they travel through the body or the interior of the earth. Now the first one, the P wave or primary wave, this is a simple compression wave. Now this type of movement can be transmitted by solids and by liquids. Now the reason why that is important is because the next one is not transmitted by liquids. It's blocked by liquids. And so the P wave, thing to remember about the P wave is that it does travel faster, so between 4 to 7 kilometers a second, while the S wave is between 3 and 4 kilometers a second. And so the P waves are almost twice as fast, but it can vary depending on the material. P waves are a compression wave, and so you have this wave vibrating back and forth in the direction that the wave is traveling, while the S wave is a shear motion. And so that's the difference in the movement of those two waves. Now we mentioned that the S waves cannot travel through liquids. The reason why that is important is because that is how we know what we know about the interior of the Earth, especially about the core. So it turns out that the core, or more precisely the liquid outer core, blocks S waves. And so if you had an earthquake on the other side of the world, you would not pick up any S waves on your seismograph because they'd be filtered out by that liquid portion of the outer core. The P waves still make it through, but they are bent and refracted as they travel through the different boundaries and different densities and whatnot of rock and other material. And so that is how we know that the outer core is liquid, and how we know some other things about the interior of the mantle and portions of the lower crust. So here we see a reconstruction of portions of the interior of the Earth. Again, we have started to get more detailed models than this, but basically this is the same technique as a sonogram. And so if you get a sonogram at the doctor's office, whether it's looking at your own internal organs or whether it's looking at a developing fetus or whatever else, that same technology we use with seismic waves. And so we can analyze the different speeds at which the same seismic waves from the same earthquake arrive at different seismic stations. We can kind of tell what regions of the crust, the mantle, the core, etc., are denser, more rigid, more liquid, or whatever, depending on how different seismic waves make it through. And it's the same technology as a sonogram, except it actually started with seismic waves. Back in the late 19th century, one German scientist deduced that the mantle has to be denser than the crust, and there has to be some different rigidities in between the two, because of a discrepancy of seismic waves that came from an earthquake in Japan and that were received by his instruments in Germany. And so that was back in the, I think, 1890s. Okay, so now looking at the surface waves. It's the surface waves that actually do most of the damage. Now the surface waves are generated as the body waves, as they reach the surface. They can't continue propagating out into the atmosphere, so they generate other types of waveforms along the surface. And these two types of motion we refer to as the Rayleigh waves and the Love waves. The Rayleigh waves are a rolling motion that is somewhat analogous to swells moving across the open sea, while the Love waves vibrate back and forth. They're similar to the S waves, but they are restricted to the surface. Now these two types of waveforms, they're named after the geologists and geophysicists that first described these types of motion. And so unfortunately the Love wave doesn't have anything to do with the 60s or the hippies. It's not that kind of Love wave. It's just named after the scientists that first described that motion. Now for how we measure and locate an earthquake. Now, although there are some devices that are able to detect earthquakes, even going back to ancient times in Greece and ancient China, etc., the earliest phases of what we could call a modern seismograph came around in the 19th century. But the first ones are rather crude, rather simple devices that were not very sensitive at all. The reason why they're not sensitive is because we didn't think they had to be. because why do you need a really sensitive device to measure this violent shaking? It wasn't until somebody who was trying not to record earthquakes, but is actually trying to measure and quantify the moon's gravitational pull on the Earth itself, and he's trying to measure the so-called earth tides. He took the basic mechanism of some of these early seismographs, made it a lot more sensitive, and was trying to record this earth tide when he accidentally recorded an earthquake in Germany. Well, the device is in Germany, but it recorded an earthquake that happened on the other side of the world in Japan instead. And what we see here, this is his actual seismogram. And so this is the earthquake of the wave that was recorded in Germany from Japan. Now, the basic mechanism of a seismograph is just a counterweight on the end of a spring. Now, the spring, again, is able to accommodate that motion. Now, as things start to move, the counterweight, because of inertia, stays mainly put, and the rest of the mechanism will move with the ground. Now, if we also have something that can record the shaking, again, the counterweight is staying in the same position in all three of those time lapses there. But if the rest of the mechanism can vibrate with the ground, and we have, in this case, a rotating drum covered in a special paper, then we can record all of the squiggles. Now, these days, this is mostly done electronically instead of through the analog method as we'd see with the old school paper seismographs. Additionally, we'd have multiple sensors set up in multiple orientations, so we could capture all the different waves, all the different vibrations in the different directions. And so this is important for things like, again, those love waves that are going side to side, and also the Rayleigh waves, which have a bit of a vertical component to it. So if you have as many different orientations, then you can capture all the different waves no matter what direction they are coming from. All right, so here's an example of a seismogram. So we might have a little bit of background noise. We'll have some kind of a marker to record, again, maybe every minute, maybe every few seconds or whichever. But then we have a strong shock. Again, this is our P wave. Remember, the P waves, they travel faster than the other earthquake waves, and so they will be recorded first. Then we have the S wave coming. Again, the S wave, it started at the same time, but it travels just a little slower, and so it'll arrive second at the seismograph. Following the S waves, we get the often more violent surface waves. And again, it's the surface waves that typically do more of the damage. Now, if you're looking at an earthquake, again, if we have the same quake in these two examples, but we have a seismograph station in one location and then a second one in another location, for the one that is more distant, there'll be a bigger gap between the P and the S waves as compared to the ones that are closer to the focus of the earthquake. And so we can tell how far away the focus or the hypocenter is, as well as the epicenter that is directly on top of it. Now, the trick is this only tells us the distance. It does not tell us the direction. And so we need more than just one or two seismographs. We actually need at least 3 or more. And so here again, we can look at the time gap in between the arrival of the P and the S waves, and knowing the speed at which those waves travel through the given rock in that region, we can estimate how far away that is. And so in this case, with an 8-minute interval, they're looking at, well, let's say that's around, say, 5,300 kilometers from the epicenter. And so if we have at least three, again, we can get the distance from each seismograph. And so one's 2,000, one's around, say 5,300, and the other's 9,000 kilometers. Again, all based on the time difference between the arrival of those P and S waves. And so in the old days, what we'd do is we'd take out a map, a paper map, and we'd draw some circles where each of the circles, the radius is the distance from that particular seismograph station to the epicenter, and where the three circles would intersect, that is the approximate location for our epicenter. Now looking at how we figure the magnitude and intensity. So how big was the earthquake actually? Now there's a difference between the magnitude of the earthquake and the intensity of the earthquake. Intensity is a measure of how strong the shaking was at any particular location. And so this uses Roman numerals going from 1 to 12, and it's ranked on what we call the Mercalli scale, or more properly, the modified Mercalli intensity scale. Now again, this is how strong the shaking was at a location, not necessarily how big the earthquake actually was. And so again, the stronger the shaking at that location, typically the greater the damage there would be. Now there's several factors that will go into determining how strong the shaking is or will be or was at any particular location. So how far away you were from the actual quake, from the epicenter, what kind of rock or sediment is underneath the location of the observer, and then what type of construction is in the building or in the other area, because again, some structures are more likely to get damaged than others. Now magnitude though, on the other hand, magnitude is looking at how much energy is actually released during the earthquake. And so this is a better way of actually ranking the quake rather than how strong was the shaking for any particular observer. We're looking at how strong the earthquake actually was and how much energy was released. So for this, we will need some data from a seismograph, and we rank this traditionally on the Richter scale, but for really big earthquakes, the moment magnitude scale is actually more precise. And we'll talk about some reasons why in a moment. But first off, for the for the modified Mercalli intensity scale, again, this is using Roman numerals going from 1 to 12. And again, it's how strong the shaking is for any individual observer or group of observers at any particular location. So for an intensity of 1, that's not felt. So if there was an earthquake, but you did not feel it, you were experiencing intensity 1 shaking, so it was not strong enough for anyone to feel it. Intensity of 2 felt by persons at rest. And so, maybe if you're laying down or sitting down, you might be more likely to feel it than if you're standing or walking. And then intensity of 3 felt indoors, hanging objects swing, vibration like passing of light trucks. And so you may have, it may feel like there's a large truck passing by or whatever. For vibration like passing of heavy trucks, so something more like a big semi or big dump truck in that case. Skipping ahead a little bit, 6 felt by all. And so it doesn't matter whether you're sitting down, whether you're laying down, standing, walking, you are going to feel it. The vibration is strong enough that virtually everybody will feel it. And under these circumstances, many are frightened and run outdoors. Skipping ahead to, let's see, intensity of 8, steering of cars affected, fall of stucco on some masonry walls, branches broken from trees. And so we're starting to get to higher levels of damage. And then this one's typically my favorite, an intensity of 9, general panic. Now, how do you quantify general panic has always been kind of a mystery to me, but I'm guessing that once you're there, you know you're there. And then skipping ahead to 12, damage nearly total. And so even some very well-built buildings may be severely damaged or even destroyed. And the vibrations, the shaking can be strong enough that objects can be thrown into the air. And so again, that is some pretty strong shaking. Now, although the Mercalli scale is maybe less scientific, it is still useful for looking at patterns of damage and also for looking at areas that were affected by earthquakes before there were lots of seismographs in some of these areas. And so in this case, back in 1886, there's an earthquake near Charleston, South Carolina, so in this area here. And we can see that, again, remembering that an intensity of 9 is experiencing general panic. So that shaded in area there that I just shaded, that region there was experiencing general panic at the time. And then the earthquake was able to be felt by persons at rest as far away as the Mississippi Valley. Okay, now for magnitude. Again, for magnitude, we need seismographs. And so a couple things we look at the amplitude of the shaking. And so how strong was the shaking actually recorded by the quake? We compensate for the distance, and we factor in period, several other factors for the waveform. We plug it into a formula, and it's on a logarithmic scale, and you plug your numbers in and you get a Richter scale number. And again, it's a log 10 scale, so every whole number going up the scale represents a 10-fold increase from that previous number. Now, this table is showing the frequency of observed earthquakes from around 1900 up until around 2000 or so. Now again, these are averages. These are yearly averages. And so of course, some years are going to be below average and some years will be above average. Now, I remember a few years back that there were some people who were freaking out because looking at news reports and whatever of coverage of earthquakes. They looked at those, tried to calculate the number of earthquakes and said, oh no, there's more earthquakes now than were a generation ago. The problem was they were looking at news reports, not actual earthquakes. And again, as we get to more sophisticated news, better communication, we're going to hear more about earthquakes on really far-flung places that a generation or two ago we just would have never heard about. But if you actually looked at the time range when they said this, it was actually below average time. And so if they're freaking out saying, oh no, there's more earthquakes, just wait until we get back to average. But if we look at average over about a 100-year period, we see that on average there is about 18 earthquakes above a 7.0 in magnitude. Now that is more than once a month. We're looking at 1 or 2 in an average month there. But we hardly hear about any of these on the news because, again, a lot of these are in very far-flung places, maybe very remote areas where there's, again, not high population densities. And so unless it winds up being a catastrophe, which, again, is some would define a catastrophe or a natural disaster when people get in the way of nature. So nature's just doing its thing, but it only becomes a disaster when people get in the way. And so it's only when a large enough number of people get in the way that any of these would wind up on the news. But in an average year, we're looking at least a dozen in most cases to usually 18 or 20 earthquakes above a 7 in magnitude. If we're looking at quakes that are not as strong, but still pretty strong, again, 6 to 6.9, 120 a year, so about 2 a week. But again, we hardly hear about any of these on the news because, again, most of these are remote areas, and unless large numbers of people are killed, you just never hear about it. Okay, now this graphic is looking at the amount of energy released for various historical earthquakes. I added in a couple here for Sumatra and Japan. So for stuff that happened in the last 10, 20 years or so. But comparing the amounts of energy released for some of these big earthquakes compared to some other phenomena. And so, for instance, if we look at the Northridge earthquake and the Kobe quake that happened back in the 90s, these both released more energy than the bomb dropped on Hiroshima at the end of World War II. If we look at some of the even bigger ones, so the Great San Francisco quake of 1906, for instance, this released a little more energy than the eruption of Mount St. Helens, and almost as much energy as the largest nuclear device ever tested, which is by the Soviet Union back during the height of the Cold War. And if we look at, again, these 3 or 4 up here, again, the ones that are above a 9 in magnitude, we're looking at, for each of those, nearly 10 times as much energy as that largest nuclear device ever tested. Now, I like to show this graphic for a few people who, again, maybe they spend a little too much time online or watching some of those YouTube videos or other stuff online, get into conspiracy theories about, some secret organization that's causing various kinds of natural disasters. And I get questions from students all the time, usually right after there is a major quake somewhere in the world, about, they read online somewhere that such and such is actually causing these earthquakes and it's not natural and all that. But the trick is, if you have something at your disposal that is more powerful than the largest nuclear device ever tested, there are easier ways to destroy a city than to cause an artificial earthquake. Now, I have to be very clear that I'm not advocating that at all. I'm not advocating destroying the city in any way, but again, if you get too much into those conspiracy theories, sometimes it helps to do a little reality check about the amount of energy we're really talking about here. Okay, now this is all of the earthquakes, or at least those around 2.5 to maybe 5 or so and above, back in 2002. The larger circles you can see mostly around the, again, Western Pacific. Those are the ones in that year that were above a 7 in magnitude. And then you can see again, there's another one up in the Himalayas, up there. And Indonesia, we're going to throw that in with the Western Pacific. But here you can clearly see there's a lot more activity along all of the plate boundaries. But the biggest quakes tend to happen along the convergent plate boundaries, and most of those are around the Pacific Ocean. Now also you can see that there is some color coding here according to the depth of the earthquake. And if we look carefully at some of these subduction zones, you can see that, for instance, let's look at this one here. For Western South America, the green highlighter doesn't show up pretty well on that map. But you can see how the earthquakes get deeper as you go into the subduction zone. So basically what we're seeing is the path of the subducting oceanic crust, and how we have some shallow quakes and then some deeper quakes and then deeper and deeper and so forth. Now again, we can throw in a little bit for some of the really shallow stuff there, but that's basically the trend we see. And again, that is just showing the path of subduction. We're seeing the path of the subducting oceanic crust, and what we refer to this is as the Benioff zone, or more properly, the Wadati-Benioff zone, after the seismologists, the two seismologists that independently discovered the same thing. And here, this is just highlighting those earthquakes that were above a 7 in magnitude. The star there, that is the largest quake for that year. I believe that one was around an 8 in magnitude. But again, this particular year, 2002, there are 13 above a 7. So technically, if our average was 18, 2002 was a below average year. Now, there is a bit of a disconnect between the amount of energy released and the Richter scale number. This is especially true as we get to the bigger and bigger earthquakes. So you can see it start to ramp up there around a 6, and then above a 7 it just goes way up. Now, because of this, the amount of energy released from very big earthquakes, so especially 7s and especially 8s and above, is drastically underestimated by the Richter scale. And so that is why they developed the moment magnitude scale. So the moment magnitude scale compensates for some of these by looking at a little more information. And so you need more detailed information about the earthquake. And so you need, for instance, information about the area of the fault plane that broke. And so you need lots of detailed information from seismographs to see all the movement along the entire surface of the fault. You need to look at the length of displacement along the fault plane. And so from the area and the length, you can get a better estimate of how much total movement there was. And you factor in the rock strength as well. And so from that, you can get a much better indicator about the total amount of energy. And so this is because this is why we do it, because the Richter scale can often drastically underestimate the amount of energy released by very large earthquakes that have longer periods of shaking. And so here, for instance, an earthquake that would rank as a 9 on the moment magnitude scale, so for instance like the 2011 Japan earthquake, would only show up as an 8.4 on the Richter scale. Now we're not doing this because we just like bigger numbers. We're trying to get a better handle on how much total energy is being released. Now, one other factor that the Richter scale will often drastically underestimate is looking at the total duration of the shaking. Now, in most moderate-sized quakes, moderate or strong, the shaking will last usually just a few seconds. And so, for instance, for the quake this spring that happened here in Utah, that, again, maybe a few of you might have been here to feel that, when I felt it here in Orem, it just felt like it lasted 2 or 3 seconds. For a larger quake, again, it might last 10 seconds or more. Really strong quakes, it might last a minute. For the Sumatra quake back in 2004, that was, again, depending on what part of the margin of error you consider to be more accurate, between about a 9.1 to 9.3 in magnitude. The shaking, the duration of the shaking lasted over 15 minutes. And so the Richter scale that just looks at the most intense part of the shaking does not factor in the total duration of the shaking. And so because of that, it can drastically underestimate how much energy is actually being involved there, which is important to understanding how the faults and how the movement of the plates actually work. And so the Richter scale will drastically underestimate what's really going on. Okay, so looking again at some different plate boundaries and different styles of earthquakes that fit in. Again, here we have the map showing all earthquakes over a 6 or 7 year period back in the 1960s. And then the bottom map is all the earthquakes that are deeper than 100 kilometers in depth, so deeper than 60 miles in depth. Now, those shallower earthquakes, a lot of them are along divergent plate boundaries, so more specifically the mid-ocean ridges. Now the mid-ocean ridges, you will have normal faults, so we can see here, on either side of the Rift Valley. And the middle of the Rift Valley is being downdropped relative to either side. Now these normal faults tend to produce shallower earthquakes that can be strong, but not as strong as what you might get at other plate boundaries. Additionally, since these are along the sea floor, you might have some seawater that is helping to lubricate some portions of the fault, and so will not build up as much strain in some cases. Now, this is similar to what we see here in Utah, or more precisely across the basin and range. And so we are here along the Wasatch. And so here it's showing the Great Salt Lake. We're just a little further south from that here in Utah Valley. And on the other side of the Basin Range, you have the Sierra Nevadas. Now, this is a very simplified view of it. But basically the idea is every valley across this region is bounded by normal faults, and the valleys are being downdropped relative to the mountains on either side. And so Utah Valley, Salt Lake Valley, etc., these are being downdropped, and that's why the valley is here. And so as a process of this happening, you're also dealing with extension of the crust. And so this region from the Wasatch Mountains in Utah all the way over to the Sierra Nevadas, this is being stretched out right now. Now there's some debate about what will happen long term, but if it continues to stretch enough, eventually we'll have a divergent plate boundary here. The bulk of the debate is, though, will it go far enough that we'll get to that point? Okay, now we also mentioned the transform plate boundary. So in this example, we're looking at a short transform plate boundary that's accommodating an offset of the mid-ocean ridges there. And so again, this side is spreading like that there. And then this other segment is spreading like that. And so we have this area over here, they're all spreading like that, and all going in that direction. But right around here, you can see that you have some that's going in different directions along that transform plate boundary. And so these are strike slip faults or transform faults. Technically, a transform fault is when it forms the plate boundary, but you might get some strike slip faults that are off of the plate boundary. But a transform fault is the plate boundary. Now, the most famous example of a transform fault, at least in this part of the world anyway, is the San Andreas. And so it connects this little baby mid-ocean ridge in the Gulf of California with this other mid-ocean ridge over here and the subduction zone that's off the Cascades of the Pacific Northwest. And so it's accommodating this difference of motion with this side going like that relative to the Pacific side that's going like that. And here we're looking at the San Andreas Fault itself. And again, this is the fault right here. This is the plate boundary between North America and the Pacific Plate. And so we have the two plates moving like that relative to each other. Now, the San Andreas is the plate boundary. but it's not the only fault in the region. And so the San Andreas, this is looking at the San Francisco area. So San Francisco is right there on that peninsula. But this is the plate boundary right here. So it just goes alongside San Francisco. But there are other faults in the region. So just across the bay, you have the Hayward Fault. And then there's dozens of other faults across the area. But the San Andreas and the Hayward Fault are the major faults in the San Francisco area. Now we mentioned the Benioff zone, or more properly the Wadati Benioff zone. Again, we're dealing with the earthquakes generated by the subducting slab of oceanic crust. And they start off relatively shallow. We'd actually have some earthquakes here, but they get progressively deeper as it follows the path of that subducting slab of crust. Okay, so looking at earthquakes and plate interiors. Now we mentioned that most earthquakes happen at plate boundaries, but we have some that happen in the interior of plates. And so these, again, not as well understood. It's possible that some of these could be ancient rift zones that never fully matured, but didn't really heal over either. And so it's a rift zone that did not become a plate boundary. It did not spread far enough for that to happen. That now represents a weakness in the interior of the plate that never really broke up. But if there's some rough spots, maybe on top of the asthenosphere, and some strain is transmitted to these rift zones, again, it might build up some of that strain there that can be released periodically. Now, these plate interior earthquakes can be very strong for a couple of reasons. One, the older rock in the interior of the plate can be fairly rigid and can accommodate lots of strain before it finally fails. Also, that more rigid rock in the interior of the plate can transmit those seismic waves much further than some of the more deformed rock that is along the plate margins. And so a best example of one of these is the New Madrid earthquake, or earthquakes, probably better put, that happened in the winter of 1811 to 1812. And so this was a series of at least 3 events that were probably each above an 8 in magnitude. These were able to be felt all the way from New Orleans all the way up north to Quebec. And so over a huge area of the continent. The shaking was so strong, it actually rang church bells as far away as Washington, D.C. And aftershocks strong to be felt lasted for over 10 years. Technically, we're still experiencing aftershocks for this today, over 200 years ago. It's just that most of them are much smaller now, and you're probably not going to feel them. And so here we're looking at some of these modern aftershocks 200 years after the main event. You can clearly see that there's some clustering there, how there seems to be some kind of a feature there and here. And this could be, again, part of an old rift system that never fully matured, but wasn't able to heal over either. Now, this is comparing the intensity of shaking on the map for different earthquakes in different regions. And so the 1906 earthquake, that was around an 8 to 8.2 in magnitude. And we compare it to the New Madrid earthquake. And so basically we're looking at areas where they experienced a comparable amount of shaking. And so even though the earthquakes were similar in magnitude, we can see that the New Madrid event was actually felt over a much larger area, or at least it had the same level of shaking over a much larger area. And then also for the 71 San Fernando earthquake, that's similar in size to what happened in 1886 in Charleston, South Carolina. And so again, in the interior of the plate, the seismic waves can travel faster and farther. Okay, now here we are here in Utah looking at, again, some of the faults. You can see all the faults there, mostly associated with the Wasatch Front. And then these are some of the earthquakes that happened over about a week period back about, well, 14, 15 years ago now. Now, the recent activity we had in Magna just this year is just a reminder that, yes, there's lots of faults here in Utah. And yeah, occasionally we do get some activity like what happened in Magna, which is roughly there-ish. But all the earthquakes I have felt in my life, I felt here in Utah. Now, of course, some of those were strong events from outside of the state, but some of those were inside the state as well. And so we're not immune to that. Now, this marks the end of part 1 for earthquakes. Be sure to watch part 2 before you do the homework.